Every night, billions of stars shine above ancient lights crossing time and space to reach your eyes. Tonight we'll share the most relaxing facts about these distant suns to help you drift into calm sleep. If you enjoy this peaceful journey, please like, subscribe and share, and tell us in the comments which kind of night sky makes you feel most at peace. Thank you for watching now. Let's begin. The night sky stretches overhead as a calm expanse of darkness, its depth marked by countless points of light that seem to shimmer yet remain still. On clear evenings, the atmosphere grows transparent enough for those distant lights to reach Earth, unchanged, their photons crossing space for years, centuries, even millennia before meeting the human eye. Every star seen from the ground is a sun in its own right, surrounded by whatever worlds or empty orbits belong to it, each one existing far beyond the faint illusion of closeness created by the dome of the sky. The air above is quiet, yet filled with the constant passage of starlight, invisible during the day but unbroken in its arrival. Beneath that light, the surface of the planet rests, turning slowly, showing one region after another to the face of space, so that the stars seem to rise and fall not because they move, but because Earth itself rotates with perfect steadiness. The sight is ancient. Long before telescopes or charts, the same slow rotation of the heavens guided travellers and farmers who had no words for fusion or gravity, only the simple knowledge that the lights returned in predictable ways. Even now, far from cities, the Milky Way becomes visible as a pale, uneven band across the darkness, a river of unresolved stars whose light blends together until individual points vanish into one continuous glow. Each pinprick is too distant to touch, yet collectively they form the quiet background of nearly every human night. What appears as stillness in the sky is in truth immense motion slowed beyond comprehension. Every star moves through the galaxy on its own path, carrying with it a system of planets, dust and invisible fields. The sun itself drifts among them at a speed of tens of kilometers each second, orbiting the galactic center so slowly that one full circuit takes hundreds of millions of years. Yet from Earth, this motion produces no sense of urgency. The pattern of the stars remains unchanged from one lifetime to the next, allowing the mind to accept the illusion of permanence. The night becomes a place where time seems suspended, where the same constellations rise generation after generation, giving the impression of a fixed and eternal order. The calmness of that illusion is part of what makes the stars restful to watch. Even those aware of their distances and movements feel comfort in the regularity of their return. Through most of human history, the brightness of stars has been constant enough to serve as a clock. The same faint cluster seen at dusk during one season will appear overhead at night a few months later and vanish before dawn as the year continues. This steady change arises from Earth's orbit around the Sun, not from the stars themselves, but it lends the night an unhurried rhythm. The constellations that dominate winter evenings yield to those of spring, then summer, then autumn, completing a cycle that matches the passing of seasons. The sky's transformations are never abrupt. They unfold with the same patient pace as growth or decay in the natural world below. To watch them is to witness a cosmic clock that measures not minutes but months and millennia. The great arcs drawn by starlight across the heavens remind every observer of scale how much larger time and space become when measured beyond the limits of daily life. When starlight enters the atmosphere, it scatters slightly, giving rise to the soft flickering called twinkling. The effect is strongest near the horizon, where air is thickest, and weakest at the zenith, where the path is shortest. In truth, the stars do not flicker. Their light is perfectly steady. The gentle fluctuations are the work of air currents, tiny variations in temperature and density that bend light unpredictably. The result is a shimmer that seems alive, as if each star breathes in slow rhythm with the night. This subtle motion, though caused by turbulence, gives the sky a kind of living calmness. The stars appear to communicate through pulses of brightness, each one unchanged in reality, yet altered by the moving air of Earth. Beyond the reach of air, the light of a star travels through a vacuum so pure that nothing dims it. In space, a single photon may move for millions of years without colliding with another particle. It keeps its color and energy until it finds a surface capable of absorbing it. When it finally reaches the planet, its journey ends in a fraction of a second against a sensor, a mirror, or a human retina. The length of that travel is beyond imagination. Even the closest star after the Sun lies more than 40 trillion kilometers away so far that its light left when early humans first shaped stone tools. Yet all these distances condense into the tiny flashes that seem to hang just above the treetops. Each flash is an ancient message repeating endlessly, unaffected by the passage of ages. The stillness of starlight is deceptive. Inside every point of light, hydrogen atoms collide with immense energy, fusing into helium-releasing radiation that pushes outward against the inward pull of gravity. This balance of forces maintains the perfect spherical shape of the star and prevents collapse. The equilibrium is neither violent nor sudden. It endures for billions of years. From the outside, no evidence of this inattention is visible. The surface of a star radiates steadily layer by layer until its energy emerges as the faint glow visible from Earth. To the naked eye, it appears peaceful. The light is a record of balance, not turmoil. Astronomers divide the sky into regions and measure the brightness of each star against a scale. But for most observers, the science fades before the experience. The sky is not a chart, but a presence. It is wide enough to quiet the mind and constant enough to calm the body. Under clear conditions, even a short glance upward replaces noise with stillness. Some find that the longer they look, the less they sense of themselves, as if the boundary between observer and night dissolves into shared quiet. This sense of immensity is not one of fear or isolation, but of gentle absorption, as if the universe, vast and indifferent, allows a moment of rest. The moon may rise and set, planets may drift among the stars, and meteors may streak for an instant, yet the overall order remains unchanged. Every night returns the same general view, the same dense band of the Milky Way, and the same scattered patterns of brighter stars. That constancy forms the foundation of nearly all human observation of the heavens. The stars endure across languages, cultures, and lifetimes. They serve no practical purpose for sleep or survival. Now, yet they continue to mark the rhythm of darkness, offering a quiet continuity between the ancient and the modern world. The constellations, once used for navigation and myth, now function as reminders of scale, silent companions in the background of human life. On nights when clouds drift across the sky, the stars vanish without a sound, and the darkness grows deeper, yet their absence is temporary. Above the moving air they shine with the same steadiness as before, unchanged by weather or time. The certainty of their return adds to their calmness. Each clear night is not a new event, but a repetition of something enduring. The light overhead connects the observer to a cosmos that is both immense and indifferent, yet quietly ordered. The stars ask for nothing, demand no belief, and reveal no urgency. They simply shine, patient and steady, through the endless rotation of worlds. Across the dome of night, shapes appear where none truly exist. Groups of stars seem to join together into patterns, their connections traced by human imagination, rather than by lines of gravity or light. Constellations fill the sky as stories written on darkness, each one depending entirely on the viewpoint of Earth. The stars that form them are not neighbours, but distant suns separated by hundreds or thousands of light years, arranged by coincidence into figures that feel deliberate. A few appear bright enough to draw the eye, while others only complete their forms through memory or guidance. These patterns once helped travellers orient themselves on land and sea, yet they were never fixed maps of reality. They are perspectives, pictures created from chance alignment reminders that even randomness can seem orderly when viewed from far away. From a different planet or angle, the same stars would scatter into unfamiliar designs, and the constellations of Earth would vanish into unrecognizable fields of light. The figures that carry names like Orion Lyra or Ursa Major are specific to this world, and this time shaped by the slow drift of stars and by the needs of the people who watched them. When the eye adapts to darkness, faint stars emerge between the brighter ones, and the supposed outlines dissolve. Each star asserts its separateness. The idea of a hunter, a swan, or a bear becomes no more than an arrangement of points. Yet the mind continues to find order in the scatter, seeing connection where none exists. This search for patterns is a natural consequence of perception. The brain links what it sees, turning random dots into constellations, faces, and paths. Through that instinct, the empty sky becomes meaningful, and the vastness of space becomes personal. The act of mapping the heavens transforms the incomprehensible scale of the universe into something familiar and calm. To trace the lines between stars is to slow the pace of thought. Different cultures looked at the same stars and saw entirely different stories. To one, a pattern might represent a river, to another, a serpent or a god. Each interpretation arose from the local experience, the course of a river, the flight of a bird, the cycle of seasons, and though the images changed, the positions of the stars did not. This stability made the constellations a calendar before clocks existed. Their appearances at particular times of the year marked planting, migration, or celebration. In that way, the night sky became both a measure of time and a reflection of culture. Generations repeated the same gestures, lifting their eyes to the same points of light and repeating the same names. Even now, when navigation depends on satellites and technology, people continue to recognize these ancient arrangements unchanged through thousands of years. The knowledge that the same constellations looked down on those who lived long before creates a sense of continuity, a quiet reassurance that the universe is stable, even as everything within it changes. The space between constellations is filled with uncounted stars too faint to be noticed without instruments. Through telescopes, the illusion of emptiness disappears, replaced by an overwhelming field of light. What seemed simple and clean to the naked eye becomes complex, dense, and unbounded. Yet the purpose of constellations was never to be complete. They were meant to simplify. They divide the sky into recognizable portions, each with a name that allows the mind to rest in familiarity. The order they impose has no physical reality, but it provides psychological stillness. By naming patterns, people reduce the scale of infinity into something that can be held in memory. This act of naming is gentler form of quiet understanding that turns chaos into calmness without altering the universe itself. The patterns of stars move slowly through time. The gravitational pull of the galaxy causes each star to drift fractionally across the sky, changing the outlines of constellations over tens of thousands of years. The difference from one generation to the next is imperceptible. The hunter's belt in Orion remains aligned, the curve of the Big Dipper unchanged. Only over immense intervals will those shapes deform into new ones, proving that the constellations are temporary, even if they seem eternal. Their gradual transformation is another rhythm of the cosmos, one too slow to disturb the present. It reminds observers that permanence in the sky is relative, a perception born of limited time. What feels unchanging during a human lifetime is in motion when measured by the galaxy. The stars slide gently through their orbits, creating new alignments that future watchers may someday rename. In the present, these changes are so slight that the constellations appear frozen. On any given night, their arrangement is as dependable as sunrise. This reliability gives the night its sense of peace. The same figures greet travelers on distant seas, the same arcs rise over mountain valleys or deserts, and the same bright stars trace the same slow paths from east to west. Even artificial lights cannot fully erase them. They remain faintly visible behind the glow, waiting for darkness to return. The quiet endurance of these patterns suggests that the universe moves according to vast unhurried laws, indifferent to human attention, yet consistent enough to inspire trust. Looking at constellations invites stillness. The eyes adjust to dim light, the pulse slows, and thought begins to follow the rhythm of the stars. Some appear in pairs or small clusters, their separations so consistent that even after hours they seem frozen in place. To study them is to practice patience because nothing changes quickly. The comfort lies in that slowness. Modern life moves through seconds and minutes. The night sky moves through centuries. Under its calm order, the sense of urgency fades, replaced by awareness of scale. Each star's light has been travelling for ages, so what reaches Earth is already a message from the past one that cannot be hurried or delayed. Even without knowing the distances involved, the viewer senses that these lights belong to something greater than the world below. Their arrangement across the heavens is not random chaos, but quiet complexity. Every point is a part of a larger structure, the spiral of the Milky Way, a galaxy, made of hundreds of billions of stars, and yet none of this is visible directly. The constellations are only fragments of that whole, faint traces of a pattern that extends beyond sight. This incompleteness adds to their calm. They hint at infinity without forcing the mind to confront it all at once. They offer a manageable portion of immensity, a way to engage with the vastness of space without being overwhelmed. At times, clouds or moonlight hide parts of the sky, breaking the familiar figures into smaller groups. Even then, the mind reconstructs the missing lines, completing the shapes from memory. The patterns live partly in imagination, maintained by recollection and habit. They exist both in the sky and within thought, suspended between light and perception. This dual existence contributes to their serenity. The constellations are real enough to be seen, yet abstract enough to drift through the mind like calm ideas. In this way, they connect the physical and the mental worlds, uniting observation with reflection. To gaze at them is to participate in a quiet tradition older than civilization, a simple act repeated in countless forms of stillness. When morning comes, the stars fade, gradually disappearing, not because they vanish, but because the light of the sun overwhelms them. Their patterns remain above the daytime sky, invisible but intact. As the world brightens, the constellations wait for the next rotation, when darkness will once again reveal their outlines. Nothing has changed in their arrangement. The same accidental patterns persist, preserved by distance and time, scattered by chance, yet bound by perception into something enduring. They remind the observer that order and calm can arise from randomness, and that what seems permanent may be only temporarily aligned. In their faint, constant glow lies a balance between chaos and structure, between emptiness and meaning. A quiet reminder that the universe, even in its vast indifference, contains endless forms of gentle symmetry. The Sun, bright and familiar, is only one among countless stars in a wide galactic community. Though it dominates the sky from Earth, its place within the Milky Way is modest, positioned about halfway between the galactic center and its outer rim. Around it, within a small region of space, lie many other suns, some larger, some smaller, all moving together through the galaxy's spiral arm like silent travelers sharing the same current. This region is sometimes called the solar neighborhood, a zone extending a few dozen light-years in every direction. It contains stars of many kinds, cool red dwarfs that barely glow yellow stars much like the Sun, and a few bright blue or white ones that burn briefly before fading. Yet even the nearest of them lies unimaginably far away. The nearest system, Alpha Centauri, sits over 4 light-years from Earth. Its light left when the first electronic signals began their journey outward from this planet, and will continue to arrive long after those signals have faded. The distance is so great that travel between stars remains beyond human reach, though the space separating them is almost empty, filled only with thin dust and the magnetic breath of the galaxy itself. In this small stellar neighborhood, the majority of stars are not solitary like the Sun. Many are bound together in pairs or groups, orbiting one another in long, graceful arcs. Binary systems are common. Some contain stars of similar mass that revolve around a shared center, while others pair a large star with a small companion, their dance measured in years or centuries. To distant observers, these systems often appear as a single point of light, their combined brightness hiding their complexity. Within them, gravity shapes motion with quiet precision. Each orbit remains stable over spans far exceeding the entire history of humanity. The space between such systems is vast, yet on the galactic scale they form a dense and intricate web. Gravity connects them all not as a net but as a subtle curvature of space guiding every star along its path around the galactic core. The Sun itself follows one such orbit, circling the Milky Way at hundreds of kilometers per second. Yet because the galaxy's scale is so immense, one full rotation takes more than 200 million years. During that time, the constellations will distort and reform, continents will shift, and species will rise and vanish. But through all those transformations, the Sun continues its smooth trajectory, a single yellow star among billions moving through the local spiral arm known as Orion. Around it, the nearby stars drift in roughly parallel motion, forming what astronomers call the local stellar flow. There is no sound, no turbulence, no boundary, only gradual change, as if the entire neighborhood drifts together through a calm cosmic ocean. When seen from outside, this region would appear faint and unremarkable. The Sun's light would merge with that of its neighbors to form one small gleam in a spiral band. Yet from within, its warmth and stability define the entire environment of the solar system. The same could be said for any inhabited world around another star. From the surface of those worlds, the home sun would seem vast and dominant, while the rest of the universe would fade into background points. Perspective turns the ordinary into the central. This quiet truth that every star could be someone else's, Sun reminds the observer that what appears singular here is part of an immense repetition. Nearby stars vary in type, color, and age, yet they share a similar origin. All were born from clouds of gas and dust that once filled this region of space. Over time, those clouds thinned as new generations of stars formed and dispersed their remnants. The Milky Way's spiral arms act like long, slow-moving waves of density, compressing gas enough for stars to form before releasing it again into the interstellar medium. The Sun and its neighbors are products of such a wave, linked not by proximity alone but by shared ancestry in the galaxy's long cycles. Some may be remnants of clusters that have since dispersed their members, now separated by dozens of light years but still moving in similar directions. Others are younger or older, born from different clouds that drifted through the same region at different times. Together they form a quiet population, a mixture of ages and compositions that reflects the ongoing evolution of the galaxy. The nearest red dwarfs, such as Proxima Centauri and Barnard's star, are small and faint, their light barely visible to the human eye. They burn slowly, conserving fuel for trillions of years, and their dimness gives them a subdued, almost hidden presence. In contrast, bright white or blue stars like Sirius and Vega radiate with much greater intensity, but live brief lives lasting only tens or hundreds of millions of years. Their brilliance is temporary, a flash compared to the enduring glow of smaller stars. This contrast defines the neighborhood. Most stars are quiet and unremarkable, while a few shine strongly enough to dominate the local sky. Despite their differences, all contribute to the smooth illumination of the galaxy, each one a node in the vast network of stellar light. Even at these scales, distances are so immense that the stars appear motionless. Only precise measurement reveals their slow drift across the sky. This motion, called proper motion, occurs as each star follows its orbit around the galactic center. Over thousands of years, their apparent positions change, gradually altering familiar constellations. From Earth's surface, the effect is invisible to the eye, reinforcing the illusion of permanence. The same faint points appear in the same places night after night, their true paths hidden by distance. This stillness is comforting, a sign of order in the vastness. The stars may move swiftly through space, but their journeys unfold too slowly to disturb the human sense of calm. Between these neighboring suns lies interstellar space, a vacuum so thin that its atoms are separated by distances greater than those between planets. Yet it is not entirely empty. Clouds of hydrogen drift there. Faint traces of heavier elements and magnetic fields weave through the void like unseen threads. Occasionally high-energy particles from supernova pass through relics of events far away and long ago. Even in such emptiness there is continuity, a subtle medium connecting one system to another. Through this space, starlight travels without resistance, carrying information about temperature, motion, and composition. Each photon becomes a messenger linking distant worlds through the quiet act of illumination. To imagine the solar neighborhood as a true neighborhood is misleading, for its residents are isolated by unimaginable distances. Communication, travel, and exchange are impossible, yet the shared motion of its stars gives the impression of collective harmony. There is no competition, no sound, no conflict, only vast separation and enduring balance. The stars do not disturb one another. Their gravity reaches far but rarely collides. Space itself acts as a buffer, allowing each system to remain stable while participating in the grand rotation of the galaxy. This stability is the quiet rhythm of the cosmos' endless motion that feels like stillness, immense distance that feels like peace. As night falls on Earth and the sky begins to darken, the brightest of these neighbors, Sirius, Altair, Procyon, rise in turn, their light crossing the same space that separates the sun from its companions. They seem near enough to touch, yet the photons arriving tonight began their journey years ago, long before the moment of observation. Each one travelled through the same interstellar emptiness, passing unseen magnetic fields, drifting clouds and invisible traces of past stars. The light carries with it no message but its own existence, proof of distance and endurance. The neighborhood glows not with noise or activity, but with the simple persistence of light that never stops moving. In that continuity lies its serenity, a cosmic stillness made not of absence but of quiet connection. The stars seem near enough to form a dome above the world, but every point of light is separated from the next by enormous distances measured not in kilometers, but in years of travel for light itself. Light moves faster than anything known, yet even at that speed it needs years, centuries, or millennia to cross the gulfs between stars. A light year is the distance that light travels in 1 year of steady motion through a vacuum, and when people say that a star is 10 light years away, they mean that its light began its journey 10 years ago. The sky is a collection of messages from the past. No star is seen as it exists at this moment. Everyone is observed in a state already gone. The effect is not something the eye can detect because the delay is too vast to imagine, but it defines all observation of the universe. Looking upward is a form of time travel carried out silently by light. The faintest stars visible without instruments may have sent their light before recorded history began, and the galaxies that appear as soft clouds in the background shine from distances so immense that their light left billions of years ago when the universe itself was young. In this way, the night sky is not a snapshot of the present, but a layered record of cosmic time, each layer overlapping the next like translucent sheets of memory. The journey of light begins deep within a star's core where fusion produces energy that travels outward through layers of gas before escaping into space. Inside, the dense interior photons scatter, repeatedly absorbed and re-emitted countless times as they attempt to move toward the surface. It can take hundreds of thousands of years for that energy to reach open space, yet once free, it races outward, unimpeded, crossing the emptiness between stars without slowing. Every ray that reaches Earth carries information. Its color reveals the star's temperature, its brightness hints at distance, and its spectrum encodes the composition of the gases that emitted it. To study starlight is to read the quiet handwriting of the cosmos. Astronomers use this light to measure not only where a star is, but what it is made of, how fast it moves, and sometimes even whether unseen planets orbit it. All of that knowledge exists within a single thread of energy that left its source long before human eyes evolved to see it. Light does not tire or fade in the vacuum of space. It spreads, growing weaker with distance, but its speed and structure remain constant. The photons that leave one star continue indefinitely unless absorbed by dust or captured by another body. Some may travel for the lifetime of the universe without ever touching matter again. In this persistence lies something tranquil. The light does not hurry, and nothing can overtake it. Its arrival is both certain and unalterable. When it reaches the atmosphere of Earth, it passes through layers of air that bend and scatter it, giving rise to twinkling or faint color shifts. What the eye perceives as flicker is not a property of the light itself, but a sign of the living planet beneath it. Through this subtle distortion, the immensity of space meets the small movements of wind and temperature at the edge of the world. To imagine these distances is to stretch comprehension beyond familiar scales. The sun lies about 8 light minutes from Earth, meaning that its light takes just under 10 minutes to arrive. The nearest star, Proxima Centauri, is more than 4 light years away. The bright star, Vega, is about 25 light years distant. The light of Deneb, among the farthest bright stars visible to the naked eye, began its journey over 1,000 years ago. Beyond these, the Milky Way itself spans around 100,000 light years from end to end. When light crosses such immensity, it does more than connect points in space. It carries the history of motion, collision, and transformation written in radiation. To look at the night sky is to receive ancient evidence of change compressed into quiet brilliance. The concept of distance in astronomy is intertwined with the measurement of brightness. A star may appear dim because it is small, cool, or distant, and only careful observation can separate these factors. Instruments measure parallax, the slight shift in a star's position, against background objects as Earth orbits the Sun to determine distance. Yet even without instruments, the eye senses that stars differ in luminosity. Some gleam sharply like Sirius, while others barely pierce the airglow. These differences tell part of the story of space. The brightest stars are not always the largest. Often they are simply nearer their light shortened in travel time. The dimmest may be enormous and remote, shining across gulfs so wide that their intensity is thinned to a whisper by the time it arrives. This fading of light across distance softens the sky's brilliance, turning it into something soothing rather than overwhelming. Time and distance together create a kind of stillness. Because light takes so long to travel, the changes that occur in stars unfold invisibly from night to night. Even those that vary in brightness follow patterns measured in days or months, not seconds. The sky's appearance remains constant to human eyes, a condition that invites contemplation. The photons that enter the eye tonight will be replaced tomorrow by others, yet the view will be the same. The slow speed of change makes the heavens seem permanent. That illusion allows rest. If the stars shifted quickly, if their patterns altered within a lifetime, the sky would lose its calming continuity. Instead, its apparent unchangeability anchors human perception of time, offering a backdrop against which life's motion feels brief and gentle. Beyond visible light lies a spectrum of radiation, invisible to the eye but equally real. Radio waves, infrared warmth, ultraviolet rays, X-rays and gamma rays all travel at the same speed, each carrying different information about their sources. Telescopes tuned to these wavelengths reveal details hidden from ordinary sight. Cold dust clouds glowing in infrared energetic particles from young stars shining in X-rays, the faint background radiation of the universe itself stretched into microwaves. Together they show that starlight is only a narrow part of a vast conversation between matter and energy. Yet even within this invisible range, the same principles hold: distance softens, time delays, and motion becomes smooth when measured on cosmic scales. The light that reaches Earth interacts briefly with the world before vanishing. Some is reflected by clouds, some scattered by molecules of air, some absorbed by land or water and converted into warmth. A tiny portion enters the eyes of living beings and triggers the sensation of sight. In that instant, energy that has travelled across space for thousands of years ends its journey in perception. The human act of seeing completes a chain that began with fusion inside a distant star. The link between those two events, between nuclear reaction and quiet observation, is almost incomprehensible in scale, yet it occurs constantly and effortlessly. Every moment of starlight on Earth is the end of a story that began long before human existence. Because the distances involved are so great, astronomers sometimes describe space as a form of history rather than geography. To look farther away is to look further into the past. The farther a star, the older the image we see. In this sense, the universe is not static, but layered in time, with near stars representing recent history and distant galaxies showing ancient epochs. This layering gives the night sky a texture of depth, both spatial and temporal. Even though the stars seem scattered randomly, they are arranged in perspective across billions of years. The mind, unable to grasp such intervals directly, perceives instead a gentle field of light, an image simplified by distance into something serene. The light that fills the night is continuous. It does not arrive in bursts or patterns, but in steady streams from all directions. It enters the atmosphere quietly, without sound touching everything equally. That evenness, that absence of interruption, is what gives the night sky its calm. The observer standing beneath it becomes part of the same continuum, an object illuminated by photons that began their voyage long before life existed on Earth. In that awareness lies a kind of peace, the recognition that time and distance, though vast, connect all things through light that never stops moving. When night falls and the air clears, the stars do not all appear the same. Some glow with a cool reddish tint, others with a warmer yellow, and a few shine white or faintly blue. These colours are not tricks of atmosphere or illusion, but true expressions of temperature. Every star emits light across the visible spectrum, yet its strongest wavelengths depend on how hot its surface is. The cooler ones radiate most of their energy as red or orange light, while hotter ones peak toward blue or violet. Between them lie the white stars, balanced across the spectrum like the sun itself. The differences are subtle to the unaided eye because the human retina is less sensitive to colour in low light, but they become clear in photographs where long exposures gather every photon. The result is a quiet rainbow scattered across the heavens, each hue marking a specific level of heat and energy. In that gradient lies one of the simplest and most soothing truths of astronomy. The universe is filled with colour, though most of it is too faint to see directly. A star's colour is more than aesthetic, it is a measure of its nature. The surface of a red dwarf glows at only a few thousand degrees Celsius, cool enough that much of its light shifts toward the red end of the spectrum. These stars burn fuel slowly and can shine for trillions of years longer than the universe has yet existed. Their light is soft, steady, and faint, dominating the galaxy not through brightness, but through sheer number. In contrast, a blue star's surface can exceed 20 or 30,000 degrees Celsius, releasing intense radiation and light that travels far through space. These stars live fast and die young, burning through their hydrogen in a few million years before collapsing or exploding into remnants. Between these extremes lie the yellow and white stars like the Sun and Vega, maintaining balanced temperatures that allow them to shine steadily for billions of years. Together, these varieties create the spectrum of the night. Seen as a whole, it is a scene of equilibrium, countless suns at different stages of life, each radiating according to its own inner balance of heat and gravity. Colour also reflects age. As a star evolves, its temperature changes and so does its light. Newly formed stars often appear blue-white, the sign of youth and energy, while older ones expand and cool into red giants, their outer layers stretched and thinned. These transitions occur so slowly that no eye could ever witness them directly. What seems like eternal colour is merely one frame in an endless progression. Even so, the relationships hold across billions of years, linking colour to life cycle in a quiet order. From the collective view of the galaxy, it is as if time itself has been painted in gradients from the blue of youth to the red of age, with long spans of yellow stability in between. When astronomers analyze starlight through instruments, they break it into its component colours to reveal hidden information. This process, called spectroscopy, transforms light into data. The dark lines and bands within a spectrum show which elements are present in a star's atmosphere, because each chemical leaves its own pattern of absorption. Hydrogen, helium, calcium, and iron mark their presence like faint fingerprints on the rainbow. From these patterns, scientists learn not only what stars are made of, but also how they move. If a star's light shifts slightly toward red, it is receding. If it shifts toward blue, it is approaching. These Doppler shifts are gentle signals that reveal the dance of the heavens, binary stars circling each other, clusters, expanding galaxies rotating. The variations are too small to see but measurable in wavelength. In this way, color becomes a language through which the universe speaks soft and continuous, its words written in light. Yet for those watching with the naked eye, color offers something simpler, a calm awareness of diversity without tension. The eye catches the warm red of Betelgeuse, the cool blue of Rigel, the golden tone of Capella, the pale brightness of Sirius. Each star stands distinct yet harmonious, contributing to the overall softness of the sky. The contrasts do not clash. They blend, muted by distance and air, until the heavens appear unified. In this balance lies the serenity of starlight. The colours coexist without dominance, forming a quiet equilibrium that mirrors the balance within stars themselves, where pressure and gravity remain in perfect opposition. Even at night's greatest darkness, the faint spectrum remains a silent display of physics expressed as beauty. Colour also reveals the relationship between stars and human perception. On Earth, colour often signals heat motion or emotion, but in the cosmos it becomes detached from those associations. A red star does not burn less fiercely than a blue one. It simply emits light differently. The scale of temperature and energy is so vast that human intuition loses meaning. Yet the brain still interprets these hues as calm or bright, warm or cool, creating emotional resonance where only physics exists. This translation between reality and perception is part of the quiet appeal of astronomy. It shows that even without direct understanding, the mind finds peace in patterns that echo natural order. Over time, the light of a star spreads outward, its colour diluted by distance. Interstellar dust scatters shorter blue wavelengths more easily, allowing red light to travel farther. This effect, called reddening, makes distant stars appear warmer in hue than they truly are. The same process gives sunsets their glow when sunlight passes through thick layers of atmosphere. In the vastness of the galaxy, this scattering softens the sharp edges of colour, blending one region into another, until the Milky Way glows as a pale even band. The sharp blue of a nearby star fades into the soft gold of another farther away. No single shade dominates. All contribute to a slow gradient across space. In star clusters, colour maps reveal population and evolution. The youngest clusters shine with blue stars that have not yet exhausted their fuel, while older ones glow red and orange as massive members fade. Seen from afar, these hues merge into a gentle composite. The galaxy as a whole radiates mostly in soft white light, a combination of countless stars of every kind. That white is not pure. It is the sum of diversity smoothed by distance. It represents balance on a cosmic scale, the blending of countless temperatures into calm uniformity. To think of the universe this way is to recognize that stillness often arises not from simplicity, but from equilibrium among many differences. When starlight reaches Earth, the eye captures only a fraction of its color. Most of it passes unnoticed, too faint or too distant. Yet even a glimpse is enough to convey scale and harmony. The quiet spectrum overhead connects every visible star to the processes that sustain it. Each hue is a signature of energy released in fusion, traveling through millions of kilometers of gas before entering the void unchanged until it meets the air of a small planet. The photons carry no meaning, yet together they form a tapestry of gentle variation. Their persistence across time and space reflects a universe where even extremes of heat and radiation express themselves through calm gradients rather than chaos. In the end, the colours of starlight remind the observer that beauty in the cosmos is not rare or fragile but constant. It exists everywhere, repeated in countless forms across the galaxy. Each color is a state of balance achieved through immense pressure and time, an equilibrium between burning and shining creation and release. The night sky, when seen as a field of hues rather than points, becomes a quiet spectrum of cosmic life, spreading from deep red to pale blue, from youth to age, from energy to rest. It asks for nothing and changes for no one, glowing softly in patterns that endure beyond understanding. In that still gradient of light, the universe reveals its gentlest face. The night sky at first appears to be filled with stars of equal light, yet a closer look reveals that some shine more strongly than others. This difference, known as brightness, is not a matter of a star's true strength alone, but of distance, size, and temperature combined. What the human eye perceives is apparent brightness, the amount of light that actually reaches Earth, while a star's real power, its luminosity, may be very different. A small nearby star can appear as bright as a giant thousands of times more energetic but far away. The interplay between distance and light defines much of what the sky seems to say. Without that perspective, the heavens would look flat and uniform, stripped of their sense of depth and scale. Instead, the variation in brightness turns the night into a textured landscape, where each glimmer suggests distance and dimension. The brightest stars catch attention first, their steady beams guiding the gaze, while fainter ones fill the spaces between, softening the sky into a continuous field. The result is both orderly and soothing brightness, balanced against dimness, nearness, balanced against remoteness. Brightness is measured through magnitudes, an ancient system still used today. The lower the magnitude number, the brighter the star appears. The difference between one magnitude and the next corresponds to a specific ratio of light intensity. Yet to the eye, the change feels natural and continuous. This scale has its roots in the work of early observers who divided stars into 6 groups by brightness, a simple classification that modern instruments later refined. Even with exact tools, the concept remains intuitive. A star of first magnitude stands out sharply, while one of 6th magnitude barely glows at the edge of visibility. Beyond that, the sky holds countless fainter stars that can only be seen with telescopes. In this hierarchy, brightness becomes a quiet measure of the universe's depth. It suggests that what is most visible is not necessarily most common, that the brilliance of a few stands upon the backdrop of the unseen many. The sun, when compared to other stars, is not exceptionally luminous, yet from Earth it is overwhelmingly bright because of its proximity. Were it moved to the distance of even the nearest stars, it would fade to invisibility without a telescope. The lesson in this contrast is simple, and calm perspective changes everything. Brightness is not an absolute quality, but a relationship between source and observer. It depends on space direction and the transparency of what lies in between. Dust and gas can dim a star's light, scattering it, until its intensity is reduced to a soft haze. The interstellar medium, though nearly empty, gently alters the light that crosses it, shaping the tone of the galaxy much as mist softens sunlight over a valley. The universe is full of such quiet filters. They do not block light completely, but temper it, turning harsh brilliance into glow. When astronomers speak of intrinsic luminosity, they refer to the total energy a star emits in all directions. This true brightness depends on temperature and size. A small red dwarf releases little energy compared to a large blue giant, yet because there are far more red dwarfs, their combined contribution to galactic light is significant. The most luminous stars are rare but visually dominant, their radiations spanning enormous distances. They serve as beacons across the Milky Way, points by which distances can be estimated. By comparing apparent brightness with expected luminosity, scientists can infer how far away a star must be. In this way, brightness becomes a ruler stretched across space, allowing the mapping of regions far beyond direct measurement. To the observer, brightness carries emotion as well as information. The contrast between a brilliant star and its dim companions creates rhythm. The eye moves naturally from one to another, tracing paths through constellations. The brightest often anchor familiar patterns, Sirius marking Canis Major Vega in Lyra Altair in Aquila. Their clarity draws attention, yet they exist within a sea of faint light that gives them context. Without that background, their brilliance would feel harsh. With it, they become harmonious. The faint stars are as important as the bright, filling the spaces that allow the sky to rest in balance. This subtle interplay mirrors natural harmonies elsewhere, the way sound needs silence to be music, or how the tides rise and fall define the shore. Brightness also shifts over time, though so slowly that the change is imperceptible. Stars move relative to Earth, their distances and alignments altering through the ages. Some grow fainter as they exhaust their fuel, others brighten as they evolve. These changes occur over spans of millions of years, invisible to individual lives but steady in cosmic terms. The stability of brightness within a human lifetime gives the illusion of permanence, which in turn gives comfort. Even though every star changes, the changes are too slow to disturb the night's calm order. To know that what is seen tonight is almost identical to what was seen by ancestors thousands of years ago connects the present to a longer continuity, a rhythm measured not by days but by epochs. Brightness also depends on the medium through which light travels. The atmosphere, though clear, is not neutral. It bends and scatters, light-making stars near the horizon appear redder and dimmer than those high overhead. Humidity, dust, and pollution can further soften the view, yet even these distortions add a layer of tranquility, blurring harsh contrasts and giving the sky a gentler character. When starlight passes through moving air, its brightness wavers, creating the subtle flicker known as scintillation. The effect, while caused by turbulence, conveys a sense of life and softness. The stars seem to breathe. This delicate variation transforms constant radiance into a visual rhythm as regular as a heartbeat. Brightness varies among entire groups of stars as well. In open clusters where many stars form together, the range of brightness reveals their different masses and stages of life. Some still shine with youthful intensity, others already fading toward quiet ends. Globular clusters densely packed with ancient stars emit a more uniform glow, their light softened by age. The collective radiance of such systems shows how the galaxy stores its light, concentrated in dense regions dispersed elsewhere in diffuse clouds. Even nebulae, though not stars, contribute to the perception of brightness by reflecting or emitting light, forming misty backgrounds that make points of starlight seem sharper. The balance between these elements, bright, faint, diffuse, creates the texture of the visible cosmos. The human eye, sensitive to contrast rather than absolute light, responds to these differences with ease. Even in total darkness, after a few minutes, it can perceive faint stars down to the threshold of sixth magnitude. This adaptation is one of the quiet marvels of biology, aligning human perception with the scale of starlight. The retina's cells, designed for dim vision, allow observers to see across light years, not by amplifying brightness, but by expanding sensitivity. In that adjustment lies another example of harmony, the small and the vast cooperating through physical law. The act of looking becomes an exchange light that has travelled for centuries, completes its journey in a single moment of awareness. The concept of brightness extends beyond observation into feeling. To many, the brightest stars carry symbolic weight, standing for constancy or hope. Yet their true nature remains indifferent to such meaning. They shine simply because the balance of fusion and gravity compels them to do so. Their brightness is neither invitation nor message, only the steady outcome of physical processes repeated everywhere in the universe. The peace they bring arises not from intention, but from reliability. These stars are as they are, their light unwavering within the scale of human life. That steadiness, so absolute and yet so gentle, turns the infinite into something intimate. When the night grows still and eyes adjust fully, the measure of brightness across the sky becomes not a hierarchy of power, but a field of quiet equilibrium, a reminder that the cosmos in all its vastness remains governed by simple, continuous light. Among the countless lights scattered across the Milky Way, the vast majority are not the large, bright, or short-lived ones that dominate images and stories, but the small, faint, and enduring. These are the red dwarfs, the quiet background of the galaxy, invisible to the naked eye, yet making up most of its stellar population. They are the ordinary stars, steady and undramatic, each one a sphere of hydrogen slowly turning that fuel into helium through nuclear fusion. Their surfaces glow at temperatures of only a few thousand degrees cool compared to the sun, giving them their characteristic red or orange color. They radiate little light, but what they emit they maintain without interruption for trillions of years. In cosmic terms, they are almost eternal. No red dwarf has yet reached the end of its life because the universe itself is not old enough for one to have done so. Their longevity makes them the quiet foundation of the stellar community, providing the slow pulse by which the galaxy endures. These stars are small, some only a tenth the mass of the Sun, yet their simplicity grants them stability. Inside them, the same process that powers all stars' fusion of hydrogen into helium occurs more gently. Because gravity compresses them less, their cores never reach the extreme pressures that drive faster reactions in massive stars. The result is a balance between energy production and loss that can last for unimaginable spans of time. Light from a red dwarf might take years to cross even the nearest regions of space, but its source will continue to shine with quiet consistency long after brighter stars have faded. The stillness of the night sky, its calm distribution of faint, distant light, owes much to these modest suns. The sun itself, though larger and warmer, shares the same steady nature. It belongs to the middle class of stars, neither small nor giant, neither brief nor eternal. Like many others of its type, it spends most of its life in equilibrium on what astronomers call the main sequence, the long central stage of a star's life when fusion remains constant. Main sequence stars vary in color and brightness depending on mass, but they share one defining quality: stability. They neither collapse nor expand drastically, maintaining shape and radiance over billions of years. This steady state is the most common condition for stars in the universe, far outweighing the brief dramatic phases that precede or follow it. In the grand scale of time, the universe is filled not with explosions but with quiet burning, not with collapse but with endurance. The quiet abundance of small stars creates a kind of cosmic anonymity. They're too faint to dominate the sky, and too stable to attract attention. Most of them remain unnamed, known only by catalogue numbers or coordinates, yet collectively they shape the character of the galaxy more than any of their brighter peers. They populate the spiral arms, drift through open clusters, and fill the regions between visible constellations. Their combined mass outweighs that of all the massive stars put together. In every direction they extend far beyond what telescopes can resolve, forming a hidden structure of light too faint to isolate, but too numerous to ignore. They are the quiet majority unseen but omnipresent. Each of these small stars is a self-contained world of physics governed by the same principles as the Sun but scaled down. In their interiors, the constant pull of gravity presses hydrogen atoms close enough for fusion to occur. The energy produced then moves outward through convection carried by rising currents of gas until it reaches the surface and radiates into space. Because red dwarfs are cool and dense, convection dominates from core to surface, ensuring that fresh hydrogen continually replaces what is used. This thorough mixing allows them to burn nearly all their fuel, leaving little waste. Massive stars, by contrast, exhaust only their central hydrogen and leave large outer layers untouched. In this difference lies the secret of the red dwarf's longevity efficiency through slowness. The smaller the star, the slower it lives, and the longer it remains stable. Though faint red dwarfs can host planetary systems, recent observations show that many possess small rocky planets within their habitable zones where temperatures could allow liquid water. Because these stars emit less light, their habitable zones lie close to their surfaces, meaning that any planets there would orbit quickly, completing a year in days or weeks. From such worlds, the parent star would fill much of the sky, a deep orange sun casting long cool light. Whether such places could support life is uncertain, for red dwarfs often produce flares, sudden bursts of magnetic energy that can bathe nearby planets in radiation. Yet between those moments of activity they return to calm. Over billions of years, their quiet persistence ensures that even with occasional disturbances they remain constant sources of warmth. Other types of common stars accompany the red dwarfs in this slow harmony. There are orange dwarfs, slightly larger and brighter, their warmth more balanced. There are white stars like the Sun burning at higher temperatures but still measured in billions of years of life. Together these stars form the framework of the Milky Way's long-term stability. They orbit the galactic center in steady paths, rarely interacting or colliding. Their slow orbits define the pace of the spiral arms, setting the rhythm of stellar generations. In the midst of this vast clockwork, rare massive stars blaze briefly, enriching space with new elements before fading, while the countless smaller ones continue their tranquil glow. The light from such stars reaches Earth as faint, steady photons that blend into the background glow of the sky. Viewed through telescopes, they appear as points barely brighter than the darkness around them. Their presence is subtle but profound. They remind observers that the universe is not dominated by grandeur alone, but by endurance. Each small star contributes to the collective radiance of the galaxy, a quiet accumulation of light spread over billions of years. If all the red and orange dwarfs were suddenly to vanish, the Milky Way would appear hollow, its great spiral dimmed and incomplete. Their cumulative glow, invisible individually, forms the soft background that gives depth to the sky. Even when considering the fate of the universe, these small stars hold significance. While massive stars will collapse into black holes, or neutron stars, and medium ones will shrink into white dwarfs, red dwarfs will continue burning hydrogen until they fade into dim blue embers. They will cool so gradually that the process will take longer than the current age of the cosmos. When that distant era arrives, the universe will be populated mainly by their remnants, faintly glowing with stored heat. In this vision, the future of the cosmos is not one of violent death, but of slow dimming, a gentle fading of innumerable small suns. The final light of the universe may come not from cataclysmic explosions, but from the patient endurance of the common stars. In every direction, beyond what the eye can see, these stars continue their quiet work. They do not flare dramatically or end abruptly. They exist in balance, transforming matter into light with unwavering rhythm. Their stillness defines the background of the night. They ask for no notice, yet they fill the galaxy with calm, steady fire. In their persistence lies the essence of cosmic peace, the idea that most of what exists in the universe does not change quickly or loudly, but holds its form across ages, maintaining equilibrium through quiet repetition. The common stars, faint and enduring, are the universe's heartbeat, slow, stable, and everlasting. Every star, whether massive or small, lives in a delicate balance between two opposing forces. Gravity, the inward pull that draws matter together, constantly tries to compress the star toward its center. Against it, the outward push of pressure from nuclear fusion resists collapse. The result is equilibrium, a quiet truce that can last billions of years. Inside this balance, a star is not static but dynamic, sustained by continuous motion. Gas flows inward under its own weight, becomes hot and dense, and through fusion transforms hydrogen into helium. The released energy then pushes outward, keeping the star stable. This balance between contraction and expansion defines the main sequence phase, the long middle period when a star neither grows nor shrinks dramatically. In this stillness lies the heart of stellar calm, a harmony of forces so perfectly matched that the entire structure appears motionless, even while its interior churns. The process begins in the core, where temperatures reach millions of degrees Celsius. Here, individual protons, the nuclei of hydrogen atoms, move so rapidly that collisions overcome their mutual repulsion. When they fuse, they form helium and release energy in the form of gamma rays and neutrinos. That energy moves outward, changing form as it travels through the layer above. In dense regions, photons scatter endlessly, absorbed and re-emitted countless times, until they reach zones where they can escape as visible light. The journey from core to surface can take hundreds of thousands of years, yet the flow remains continuous. Each layer of the star supports the next passing, along the pressure needed to prevent collapse. The result is a perfect feedback loop. Gravity confines the fuel, fusion creates the heat that sustains the structure, and the radiation maintains the outward push that keeps everything in shape. This state of balance is self-correcting. If a star were to contract slightly, compression would increase the temperature and rate of fusion, releasing more energy and pushing the layers back outward. If it expanded too much, the temperature would drop, reducing fusion and allowing gravity to pull inward again. The star adjusts automatically, returning to stability. The system behaves like a vast natural regulator, ensuring that change occurs gradually. This is why the sun's brightness remains constant to within a fraction of a percent across centuries, and why most stars on the main sequence display the same quiet steadiness. Their apparent stillness is the outward expression of deep, perpetual equilibrium. In this balance, nothing is wasted. The fusion of hydrogen into helium releases energy with exceptional efficiency, converting a small portion of mass directly into light. Over billions of years, that light radiates outward, warming any nearby worlds and illuminating the galaxy. Yet compared to the total mass of the star, the energy released at any moment is tiny. This restraint is what allows longevity. The core's reactions proceed at a controlled pace, just fast enough to counter gravity and no faster. The laws of physics provide this balance inherently without design or intent. It arises naturally from the conditions of matter under pressure. When those conditions change as fuel depletes, or the star gains or loses mass, the balance shifts, leading eventually to new stages of evolution. But during the long span of equilibrium, a star lives in quiet perfection. The outer layers of a star reflect the stability of its core. Heat from the center causes gases to rise and fall in convection, currents creating granules and patterns visible on some surfaces through telescopes. On the Sun, these appear as tiny cells of brightness and shadow, each lasting only minutes, yet collectively maintaining uniformity across the disk. Larger regions, such as sunspots, mark localized imbalances where magnetic fields temporarily inhibit the flow of heat. Even these disturbances occur within limits governed by the same fundamental equilibrium. They are small ripples on the surface of a system that otherwise remains steady for eons. Beneath them, the fusion reactions continue unchanged, indifferent to surface fluctuations. The stability of the whole ensures that no single disturbance can alter the star's overall behavior. The scale of energy within a star is beyond human comprehension, yet its manifestation is gentle. The Sun releases more power every second than all of human civilization could produce in millions of years, but the energy spreads across space so widely that it arrives on Earth as a soft, sustaining glow. This transformation from extreme density to quiet light is the essence of stellar balance. The violence of atomic collisions becomes the serenity of sunshine. Inside the Sun, the conditions are so intense that matter exists not as solid liquid or gas, but as plasma, a state where electrons and nuclei move freely. Yet from that chaos emerges stability, the same balance that governs every ordinary day. The relationship between pressure and gravity not only sustains stars but shapes the structure of galaxies. In massive stars, the equilibrium point lies at higher temperatures, leading to faster fusion and shorter lifespans. In small stars, it settles at lower temperatures, producing slower reactions and longer endurance. The diversity of stellar behavior across the universe stems from variations in this single principle. No matter the size, each star seeks the same harmony. The equations describing this balance are universal, applying equally to the nearest red dwarf and to the brightest giant visible across the galaxy. This shared physics connects all stars into one great system, each a node of order in the vast, otherwise empty expanse. Occasionally, the balance within a star is perturbed by external forces. A close companion in a binary system may draw material away, altering pressure and heat. The transfer creates new equilibrium points, sometimes leading to bursts of brightness or steady oscillations. Yet even in such systems, the underlying laws remain constant. The stars adjust to their circumstances, reshaping themselves until the forces again align. The cosmos allows no permanent chaos. Even disturbances resolve into new forms of stability. Over long enough timescales, every variation becomes part of a broader pattern. For planets orbiting these balanced stars, this stability is essential. The consistent output of light and heat makes possible the slow evolution of environments and life. The Sun's unwavering luminosity allows Earth's climate to remain within ranges that sustain oceans and atmosphere. The same principle likely holds for countless other worlds around other stars. Stability, not change, fosters complexity. The balance that keeps a star in shape becomes the foundation for order elsewhere. Without it, the galaxy would be a flickering sea of instability, rather than the calm field of light that fills the night. Eventually, equilibrium cannot last forever. As hydrogen in the core is gradually converted to helium, the internal conditions evolve. Gravity begins to gain the upper hand, compressing the core until new reactions begin. The balance shifts toward transformation, and the star's next stage begins. But these changes unfold slowly over spans of time beyond any human measure. For most of its life, a star remains in quiet harmony, shining with the same steady rhythm day after day, century after century across billions of years. To look at a star is to see balance, embodied matter and energy held in perfect proportion, motion and rest intertwined. Its calm radiance across space is the visible signature of that symmetry. In its light, the universe appears orderly, patient, and complete. While many stars appear perfectly constant, some display slow and graceful changes in brightness, like the rhythm of breathing across cosmic time. These variations, known as stellar variability, occur for many reasons, yet most follow predictable cycles. Some stars expand and contract slightly, causing their luminosity to rise and fall in steady pulses. Others brighten or dim because they are part of pairs or systems, where one periodically passes in front of the other. The changes unfold over days, months, or years, never abrupt or chaotic, but rhythmic and dependable. To the naked eye, only a few of these stars reveal their variability clearly, yet instruments record countless examples throughout the galaxy. Each one serves as a reminder that even within stability, there is movement, that stillness often contains its own quiet oscillation. The sky's peace does not depend on immobility, but on repetition so vast that it feels eternal. The most well-known pulsating stars are Cepheids, large and luminous suns many times bigger than the Sun. Their outer layers expand and contract in regular cycles controlled by the balance between radiation and gravity. As they swell, their surfaces cool and dim. As they contract, they heat and brighten. The entire process repeats with exquisite precision, each star keeping time as if guided by an internal clock. These cycles can be measured with such accuracy that they serve as cosmic yardsticks. The period of pulsation corresponds directly to intrinsic brightness, allowing astronomers to calculate distance by observing how long the rhythm takes. In this way, gentle variability becomes a tool for mapping the universe. Yet beyond its scientific use lies something more tranquil. Cepheids breathe light into darkness with serene regularity, their brilliance waxing and waning over weeks as if the universe itself were inhaling and exhaling. Smaller variations occur in stars that rotate unevenly or carry magnetic fields. Dark spots cooler than surrounding areas move across their surfaces, causing slight changes in brightness as the star turns. The Sun itself follows this pattern with sunspot cycles repeating roughly every 11 years. These fluctuations are subtle, influencing the total energy output by less than 1%, yet they shape the long-term climate of nearby planets. From a cosmic perspective, they are whispers, tiny modulations in otherwise steady light. To study them is to witness balance maintained through motion, not through stillness. The Sun's consistency is not the absence of change, but the sum of countless regulated variations, each part of a vast natural rhythm. Another form of variability arises from companionship. Many stars exist in binary systems where two or more orbit a shared center. When their orbits align with our viewpoint, one may pass in front of the other, briefly dimming the combined light. These are eclipsing binaries among the most serene manifestations of stellar motion. Their light curves, graphs of brightness over time, show smooth, predictable dips that repeat with mathematical precision. To observers, each eclipse is like the slow closing and opening of an eye across space. No chaos disturbs these patterns. Gravity holds the orbits in perfect order, turning motion into a clock. The best-known example, Algol in Perseus, dims for a few hours every few days, as its fainter companion crosses in front, then brightens again, with the same reliability it has maintained for millennia. Even variability here becomes a form of consistency, a reminder that change itself can be steady. Not all variations are so regular. Some stars fluctuate irregularly due to turbulent processes in their atmospheres or the influence of surrounding dust. Yet even in these cases, the transitions remain slow and continuous, measured in the rhythm of months or years. Red giants, for instance, often pulse in complex patterns as their outer layers expand and cool. Their light swells and fades softly, sometimes overlapping cycles that create gentle beats like overlapping waves. These stars nearing the end of their lives seem to communicate their age through this quiet flickering, as if their energy were sighing outward into space. Though the causes are physical changes in temperature, pressure, and opacity, the result is visual poetry, the transformation of internal physics into a visible pulse. To an observer watching night after night, these variations unfold too slowly to startle. The brightness of a star does not leap or flash, but drifts through gradual shifts. The patterns persist so consistently that ancient astronomers noticed them long before telescopes existed. Records from thousands of years ago mention stars that change their light, and modern instruments confirm those same rhythms today. Such continuity across civilizations emphasizes the gentle permanence of variability. A star that dimmed for one generation brightens again for the next, unhurried, indifferent to time. In its cycle lies both change and constancy, a paradox that captures the essence of the cosmos. Variability also occurs in entire clusters of stars where gravitational interactions or waves of star formation cause regions to shimmer differently over time. When thousands of stars vary together, the effect can resemble a slow ripple of brightness moving across the galaxy. These shifts are not visible to the naked eye, but detected through precise measurements of light. They reveal that the universe, far from static, is alive with quiet oscillations, structures expanding, contracting, and breathing in unison over spans too long for human awareness. The night sky appears calm because the timescales of its movement stretch beyond human perception. To us, the universe feels still, though it is constantly in motion. Variable stars have long guided exploration not only across physical space, but also through understanding. Their steady patterns help calibrate distances, determine the size of galaxies, and measure the expansion of the universe itself. Yet beyond their scientific significance, they convey something elemental about balance and transformation. They show that order does not require stasis, that serenity can include gentle motion. Just as a heartbeat signals life without disturbing calm, so do these fluctuations demonstrate the vitality of stars. They are expressions of equilibrium sustained through rhythm. Even in systems where variability leads eventually to change, where mass is exchanged, or where stars evolve toward new states, the process unfolds gradually. Binary companions spiral together over millions of years, their light blending and fading only after long ages. Pulsating stars expand until fusion shifts balance, and then settle again into temporary stillness. Nothing in these cycles is abrupt on the scale of human experience. Each transformation honors the same principle of cosmic patience. The stars remind observers that continuity is not the absence of difference, but its repetition across incomprehensible spans of time. For those watching the sky, the awareness of these gentle fluctuations can deepen the sense of rest they inspire. Knowing that even the steadiest stars breathe slightly, that their calm hides slow motion, adds a layer of quiet understanding. The universe is not frozen but poised, alive yet tranquil. Every soft pulse of brightness marks a balance, maintained, a system adjusting within natural bounds. When the eye sees a star's faint flicker, it is witnessing a dialogue between gravity and light mass, and pressure expansion and contraction. These exchanges continue endlessly, not to create drama, but to preserve peace. Across the galaxy, trillions of stars perform this subtle rhythm, each one holding its place within the grand harmony of motion. In their steadiness and their variability alike lies the same message that change, when measured across eternity, becomes indistinguishable from stillness. Every star begins as a faint disturbance inside a cloud of gas and dust, an invisible seed within an immense and silent nebula. These clouds drift through the spiral arms of the galaxy, vast structures made mostly of hydrogen, laced with traces of heavier elements and fine particles of interstellar dust. From afar they appear motionless, but within them gravity works patiently, drawing denser regions together. The process unfolds slowly over millions of years, as small irregularities cause matter to gather. When enough material accumulates, a fragment of the cloud collapses under its own weight, compressing and heating as it shrinks. There is no sound, no flash, no explosion, only a gradual tightening of gas into form. The beginning of a star is not violent but quiet, shaped by balance and time. Inside these collapsing regions, pressure increases until the core becomes hot enough for hydrogen atoms to collide and fuse into helium. This moment marks the true birth of a star, when fusion ignites and energy begins to flow outward. Before this point, the object is called a protostar, hidden within a cocoon of dust. It glows faintly in infrared light, but remains invisible to ordinary sight. Surrounding the growing star, the rest of the cloud flattens into a rotating disk, a natural consequence of angular momentum conserved as the gas falls inward. Within that disk, matter begins to clump again, forming planets, moons, and smaller debris. The entire system emerges from the same quiet process collapse-heating balance. The light of a newborn star slowly clears the surrounding dust, illuminating the cavity it has created and revealing the nebula from within. In regions where star formation is active, such as the Orion Nebula or the Eagle Nebula, thousands of stars are born together. Their collective radiation sculpts the remaining gas into filaments, pillars, and waves. Yet even these grand structures evolve gradually. The pressure of starlight and stellar winds pushes outward, dispersing the nebula over millions of years, until only clusters of young stars remain shining freely against the dark. The shapes captured in telescopes, the columns and arches of glowing gas, are temporary patterns carved by balance between expansion and containment. Every wisp of light is the trace of hydrogen recombining with electrons after being ionized by nearby heat. It is a slow, continuous dance of energy, one that appears motionless on human timescales, but defines the pace of galactic evolution. A newborn star passes through several stages before settling into main sequence stability. As the protostar contracts, its rotation speeds up, and magnetic fields arise, channeling material from the disk onto the surface. Jets of plasma sometimes emerge from the poles, thin beams of light stretching for trillions of kilometers. Even these phenomena, which seem dynamic in photographs, unfold with measured rhythm. The flows persist for thousands of years, driven by gentle imbalances between gravity and magnetic tension. Eventually, as the disk dissipates and fusion stabilizes, the star reaches equilibrium. It begins its long life of steady light, a transformation so gradual that no single moment can be called the beginning. The diversity of stars originates in these early stages. The amount of mass gathered during collapse determines everything that follows: temperature, color, lifespan, and fate. A small clump produces a cool red dwarf. A large one creates a hot blue giant. The process is governed entirely by physics, yet it yields endless variety. In the same nebula, one region may give rise to hundreds of faint stars, and another to a single massive one whose radiation dominates its surroundings. The balance between fragmentation and cohesion decides how the material divides. The smallest fragments never ignite fusion at all. They remain as brown dwarfs glowing dimly with residual heat. The largest shine with fierce intensity for only a few million years before exhausting their fuel. Between these extremes lies the calm majority destined to live in steady equilibrium for billions of years. As the new star matures, its radiation begins to clear the remnants of its birth cloud. The light pushes away fine dust, forming expanding shells that gradually dissolve into the interstellar medium. What was once dense and opaque becomes transparent, revealing a young cluster to the galaxy. The surrounding space, enriched by earlier generations of stars, provides material for future cycles of formation. In this way, the galaxy sustains a quiet rhythm of renewal. Each generation of stars contributes to the next, adding heavier elements through winds and supernova seeding the clouds with the ingredients for new suns and planets. The process has continued for billions of years and will continue for billions more, a perpetual balance between creation and dispersal. Though the birth of stars occurs in places of darkness, the outcome is light. The same dust that hides a forming star also reflects and scatters its glow once it emerges, producing the soft hues of reflection nebulae. Blue light scattered more efficiently gives these clouds their pale colour. Other regions emit their own light, glowing red or pink, where hydrogen recombines after ionization. Together they form some of the most tranquil vistas in astronomy, fields of gas gently illuminated by newborn suns. The light spreads through space at its own pace, unaffected by the silence of its surroundings. There are no edges, only fading gradients where brightness melts into shadow. Even after a star stabilizes, it remains connected to its place of origin. The cluster of siblings formed alongside it drifts apart over time, dispersed by gravitational tides. Yet for millions of years they remain near one another, moving together through the galaxy as loose families of light. The Sun likely began its life in such a cluster around 4.5 billion years ago. Its siblings have long since scattered, but traces of their chemical signatures may still be found in nearby stars. This shared ancestry emphasizes that no star is entirely solitary. Each arises from matter shaped by earlier generations and contributes in turn to the next. The galaxy's calm continuity depends on this endless recycling. From the perspective of time, star formation is both fleeting and enduring. Individual stars take millions of years to form, but persist for billions, while the nebulae that create them dissipate after only a short cosmic moment. This rhythm of appearance and disappearance maintains equilibrium in the Milky Way. Even as one cloud fades, another condenses elsewhere, ensuring that the galaxy never grows completely dark. The balance between birth and emptiness keeps its spiral arms alive. From Earth, this balance is seen not as motion, but as quiet permanence. The soft background glow of hydrogen gas that stretches across the sky, faint yet persistent, the signature of creation always ongoing. The birth of a star is not a singular event, but a continuum. It begins as a faint compression in cold gas, and ends as steady radiance with no sharp boundaries between phases. Every stage is governed by the same laws, gravity pulling inward, pressure pushing outward, energy finding equilibrium. These processes require no intervention and no design. They simply unfold wherever matter and time coexist. The result is the gentle filling of the galaxy with light, one small point at a time. In every direction, new stars continue to emerge, each repeating the same quiet sequence. The universe grows not through sudden bursts, but through the constant murmur of forming suns, a process so slow and serene that it resembles eternal stillness. Once a star stabilizes and fusion in its core reaches balance, it enters the longest and calmest phase of its existence, known as the main sequence. During this time, which can span billions or even trillions of years depending on the star's size, little appears to change. The outward flow of energy from the core perfectly matches the inward pull of gravity, and the star shines at a steady brightness, maintaining its shape and temperature. This long Middle Age is the era of serenity in a star's life, the period when its processes are so finely tuned that its appearance remains constant for eons. For stars like the Sun, this phase lasts roughly 10 billion years, an interval far longer than the age of human civilization, and even now the Sun is only halfway through its tranquil journey. Inside the star, the core continues its quiet fusion, turning hydrogen into helium atom by atom. The reactions are governed by probability, with only a tiny fraction of particles fusing at any given moment, yet across the entire core, the collective effect is immense. Energy released as gamma rays takes hundreds of thousands of years to reach the surface, where it escapes as visible light and warmth. From this steady production arises a consistency that makes life possible on surrounding worlds. Without such enduring equilibrium, climates would shift too rapidly, and planets would face chaos rather than gentle evolution. The middle age of a star provides a stable stage upon which other processes, including biological ones, can unfold. The outward appearance of a main sequence star betrays nothing of the intense processes within. Its surface, though composed of plasma at thousands of degrees, changes little over time. Small fluctuations like sunspots or flares mark local disturbances but never threaten the overall steadiness. The star's magnetic field, generated by the motion of charged particles within its interior, occasionally twists and releases energy in the form of flares, but these events are transient ripples on an otherwise calm sea. Even the most active stars maintain an underlying constancy, their light unwavering when viewed across centuries. To the eye, their stability seems absolute. As millions of years pass, subtle changes accumulate. In the core, helium gradually replaces hydrogen, increasing density and temperature. The fusion rate slowly rises to compensate, and the star's outer layers expand slightly while its brightness increases. For a star like the Sun, this brightening occurs so slowly that its effect is imperceptible across human or even geological time. Over billions of years, however, it will gently alter the climate of any nearby planet, shifting boundaries of habitability. Yet this is still part of the star's calm existence, a slow adjustment rather than a disruption. Stellar evolution at this stage is a lesson in patience, the unfolding of change at a pace that defines the rhythm of the cosmos. In open clusters where stars of different masses share a common origin, this gradual aging can be seen as a pattern. The most massive stars exhaust their hydrogen quickly and evolve into giants, while smaller ones remain on the main sequence. When observed together, these clusters display a smooth gradient of color and brightness, forming what astronomers call a main sequence turn-off. The concept captures the quiet logic of stellar time. Each star follows its own path, determined solely by mass, yet all adhere to the same underlying progression. The image of such a cluster is one of orderly variety, each star at its own stage of balance, collectively illuminating the principle of continuity. The middle-age stability of stars extends far beyond individual systems. It defines the luminous texture of galaxies themselves. The soft white glow of the Milky Way seen across the sky is produced not by violent or short-lived phenomena, but by countless ordinary stars quietly shining through their main sequence lives. Their combined light is the sum of equilibrium. In that sense, the galaxy's radiance is not a sign of activity, but of peace, a reflection of innumerable stable processes continuing in unison. The light reaching Earth tonight likely comes from stars in this very phase, each one a distant example of balance perfected. For the Sun, and for others like it, this period also nurtures the conditions for life. The steady flow of energy allows atmospheres to form water, to remain liquid, and chemical reactions to persist. Without the predictability of main sequence stars, complexity could not endure. The rhythm of days and seasons on planets like Earth reflects the regularity of their parent stars. The quiet fusion of hydrogen in the core becomes at great distance the warmth of oceans, the movement of air, the growth of forests. In this way, the stillness of stellar middle age sustains motion and diversity elsewhere. The contrast between cosmic serenity and planetary change reveals the link between stability and transformation. A star's constancy makes life's variability possible. Despite the tranquility of this era, subtle internal processes continue. In the Sun, energy moves through two main layers, a radiative zone where photons scatter and a convective zone where gas circulates. The border between them generates magnetic fields that wax and wane over cycles of years. These magnetic shifts produce patterns like solar maxima and minima, influencing the intensity of solar winds and auroras on nearby planets. Yet the overall balance remains untouched. Even during heightened activity, the Sun's total output changes so little that the difference is barely measurable. The system self-regulates, restoring equilibrium after each fluctuation. When observed across cosmic time, this steadiness is extraordinary. Main sequence stars represent a phase so long that entire civilizations could rise and fall without perceiving any difference in their light. The concept of age becomes abstract when measured against such spans. The Sun, for instance, has already burned for more than 4 billion years and will continue for roughly as long again before its core composition changes enough to end this phase. To imagine that longevity is to confront the scale of stellar patience. 1 billion years to a star is no more than a season in its life cycle. Eventually, however, even this calm cannot last indefinitely. When hydrogen in the core is finally exhausted, fusion will shift outward into surrounding shells, and the delicate balance will begin to change. The star's outer layers will expand, marking the transition into its next stage as a red giant. Yet the movement toward that transformation is so slow that it will occur long after everything now living is gone. For now and for uncounted generations to come, the Sun and its peers remain in balance, quietly maintaining the structure of the solar system. Their light continues to arrive every morning as it has for ages, unchanged and unhurried. The main sequence is the true measure of cosmic peace. It is the phase in which the universe spends most of its visible life, the state to which matter naturally returns after birth and before decline. The soft light of distant stars unblinking through the darkness represents this long equilibrium. To look upon that light is to witness stability refined by time, the gentle hum of fusion holding gravity in check, the balance between pressure and weight sustained across eternity. The middle age of stars is not marked by drama or decay, but by constancy. It is the steady heart of the cosmos beating so slowly that its rhythm defines the ages of galaxies. As hydrogen in the core of a star is slowly depleted, equilibrium begins to shift. The center contracts under gravity while the outer layers expand, and the steady calm of main sequence life gives way to a new form of balance. The change is slow, extending over millions of years, but eventually transforms the star into a red giant. Its surface cools and reddens while its size grows hundreds of times larger. To nearby planets, the star appears enormous and gentle, a sphere of diluted light filling much of the sky. Yet despite its immense size, its glow softens rather than intensifies. The expansion spreads the same energy over a greater area, turning once brilliant white light into deep, calm red. In this way, the end of a star's active life begins not with violence, but with diffusion. Energy continues to flow, but its expression becomes broader and quieter, like the fading of a warm fire rather than its extinction. Inside, the core conditions grow more complex. as helium accumulates, pressure and temperature rise until new reactions begin fusing helium into carbon and oxygen. The process produces bursts of energy that stabilize the star again, holding it in a new equilibrium. This second balance is less steady than before, yet it can persist for hundreds of millions of years. During this time, the star's outer layers drift outward, carried by slow winds that remove mass into space. These stellar winds are not storms, but gentle outflows moving at speeds that seem great by human standards, yet insignificant in cosmic terms. Each particle that leaves carries with it a trace of the star's history, enriching the surrounding medium with new elements. Over time, this quiet shedding of material becomes a gift to the galaxy, providing the ingredients for future stars, planets, and perhaps life. From the perspective of a nearby world, this phase would unfold in silence. The daylight would change hue, becoming orange, then red, then dimmer as the atmosphere scattered the softening light. The star's vast expansion might swallow inner planets, while those farther away would experience new warmth. None of this would happen suddenly. The changes span time so immense that even entire species could emerge and vanish during a single transition. The fading of a star is a process too gradual to feel like decline. It is a slow release, an unwinding of energy gathered over billions of years. The outer layers, no longer tightly bound, become increasingly unstable. Pulsations develop as gravity and pressure struggle to maintain equilibrium, and the star begins to breathe, expanding and contracting on scales of months or years. Each pulse lifts more material into space, and eventually the outer shell drifts free, forming a glowing cloud of gas known as a planetary nebula. These nebulae, named before their true nature was understood, are among the most beautiful structures in the galaxy. From Earth they appear as circular or elliptical shells, with intricate filaments and soft colours, illuminated from within by the remaining core. The gases shine with emission lines of oxygen, nitrogen and hydrogen, producing pale greens, blues and pinks. Despite their appearance, these clouds are exceedingly thin. A cubic centimetre may contain only a few atoms. They expand outward at tens of kilometres per second, yet the process remains serene when viewed against the backdrop of cosmic time. The nebula's glow persists for tens of thousands of years, before dispersing into the interstellar medium, merging with the raw material from which new stars will form. At the centre of each nebula remains a small, brilliant core, the remnant of the original star's heart. For most stars, including the Sun's future, this remnant becomes a white dwarf, a sphere no larger than Earth, but with mass comparable to that of the Sun. It shines not through fusion, but through residual heat cooling slowly over billions of years. A white dwarf radiates softly, its light pale and pure, fading imperceptibly over time. The atoms inside are packed so closely that matter exists in a degenerate state, supported not by thermal pressure, but by quantum effects that prevent further collapse. This delicate balance allows the remnant to endure for ages beyond imagining. In its quiet persistence, it represents the final expression of stability, a structure no longer generating energy yet refusing to vanish. The transformation from main sequence star to white dwarf is one of gentle inevitability. The energy that once maintained outward pressure has been spent, but the memory of equilibrium remains in the remnant's form. Gravity continues to act, but it can no longer overcome the resistance of compressed matter. The result is stillness, no more fusion, no more expansion, only gradual cooling. Over eons, the white dwarf's glow diminishes to invisibility, leaving behind a black dwarf, a theoretical endpoint so faint it merges with the surrounding darkness. None yet exist because the universe is not old enough for any white dwarf to have cooled so completely. When they do, They will represent the final stage of stellar peace matter, fully at rest temperature uniform, no longer radiating but still existing. For stars of greater mass the path differs but retains the same rhythm of release. Though several times the Sun's mass pass briefly through more complex stages, fusing heavier elements in successive shells, until reaching iron where fusion can no longer yield energy. At that point equilibrium finally fails and the core collapses. The resulting explosion, a supernova, is the only true violence in the life of a star, yet even it serves a quiet purpose. The blast disperses material rich with heavy elements into the galaxy, seeding new clouds for future generations. The shock wave expands, then slows, fading into faint remnants that cool and blend with the surrounding gas. What begins as brilliance ends in stillness, and from that stillness new stars are born. The overall cycle is one of conservation. Nothing is wasted. Every element forged within a star's core is returned to space to be incorporated into something new. The carbon in living organisms, the oxygen in air, the calcium in bones all trace their origin to stars that ended their lives this way. The peace of fading light is not destruction but renewal. It marks the transfer of matter from one form of stability to another. The slow dispersal of stellar material ensures that the galaxy remains dynamic, yet calm, a balance of loss and creation repeated endlessly. Even as a star fades, its legacy endures in the light that continues to travel through space long after its source is gone. Photons released near the end of its life will cross the galaxy for thousands of years before reaching distant eyes. For those who observe them, the star will still seem alive, still shining quietly in the sky. This lingering presence extends the life of light itself, turning the act of fading into continuity. A star's end, therefore, is never abrupt. It is a transformation that leaves traces in both matter and perception. The universe absorbs these remnants without noise, folding them back into the calm rotation of its arms. The peace of fading light is not a conclusion, but a transition, a gentle passing from one equilibrium to another, ensuring that the cosmos remains both active and serene. When the final layers of gas drift away and the nebula fades into the dark, what remains of a once luminous star is a dense shining remnant, a white dwarf. Though no larger than Earth, it contains mass comparable to that of the Sun, packed so tightly that a teaspoon of its material would weigh tons. Yet this density produces no outward drama. Instead of collapse or explosion, the white dwarf rests in perfect stillness, supported by a subtle pressure that arises from the quantum nature of its electrons. This resistance, called degeneracy pressure, halts gravity's inward pull and creates a new unchanging balance. It is the last quiet compromise between matter and gravity, a form of peace achieved through compression rather than motion. From afar, the remnant appears as a tiny, brilliant point of white light, a ghost of its former star radiating the leftover heat of billions of years. The cooling of a white dwarf is an exceptionally slow process. With no ongoing fusion to replenish its energy, it glows purely from stored thermal heat. Over time, the radiance softens from white to yellow, then to red, and eventually to invisible infrared. Each stage takes longer than all of human history multiplied many times. The faint light of an ancient white dwarf represents an age beyond comprehension, the echo of a life once full of energy, now distilled to quiet persistence. When it finally cools to near absolute zero, it will become a black dwarf, cold, dark, and undetectable. Yet because the universe itself is only about 14 billion years old, no black dwarfs yet exist. All known remnants continue to glow faintly in the night, their silence unbroken. White dwarfs are scattered throughout the Milky Way, relics of stars that once illuminated the spiral arms. In dense clusters they accumulate like embers, forming fields of faint points that shimmer weakly against the blackness. Their light lacks colour, yet each carries a story written in temperature and composition. Some show traces of carbon or oxygen on their surfaces, the ashes of fusion exposed by cooling. Others display thin layers of helium or hydrogen that survived the star's earlier phases. The diversity among them speaks to the quiet complexity of stellar endings, where every path converges towards stillness, but arrives by different routes. The youngest are hot and bluish-white, the oldest barely distinguishable from the background glow of the galaxy. Together they form a hidden population, the afterlife of stars continuing to shape the faint light of the cosmos. Occasionally a white dwarf exists in companionship with another star orbiting in mutual gravitation. In such pairs new and subtle interactions occur. If the companion expands as a red giant, its outer layers can spill onto the white dwarf's surface, forming a thin shell of hydrogen. When this layer grows dense enough, it ignites in a brief flash, producing a nova, a sudden brightening visible across great distances. Yet even this is not destruction. The flash releases energy, the layer disperses, and the white dwarf returns to its steady glow, unchanged at its core. The process can repeat many times over millennia, each eruption, a minor breath of energy in an otherwise quiet existence. Only in the rare case where too much matter is gathered does balance fail, leading to a type of supernova that obliterates the remnant entirely. But most white dwarfs avoid such extremes. They remain eternal witnesses, dim and patient, drifting through the galaxy with no further transformation ahead. The light of a white dwarf is delicate, uniform, and unwavering. Viewed through telescopes, it shines without flicker, unaffected by the turbulence of atmosphere or motion. The purity of its glow arises from the absence of internal fusion. There are no turbulent convection zones, no magnetic fields of consequence, no cycles or flares. Its atmosphere, composed of thin layers of pure elements, is perfectly calm. Even the faint radiation it emits travels outward evenly, as though the star has finally reached the peace that eluded it during its active life. The surrounding space grows cold, the nebula long dispersed, till only the small core remains suspended like a solitary pearl in the dark. The stillness is profound. Nothing changes rapidly now. Time for a white dwarf is vast and nearly meaningless, its temperature declining imperceptibly over epochs that dwarf the lifetimes of galaxies. Despite their faintness, white dwarfs play a crucial role in the balance of the universe. They preserve the matter forged in earlier generations of stars, acting as long-term storage for carbon, oxygen, and heavier elements. Some will drift through space until captured again by other systems, contributing to new formations. In a sense, they are the seeds of future cycles' remnants that ensure continuity. The galaxy's chemistry evolves through their presence even when they no longer shine brightly. This recycling of matter is one of the calmest yet most profound exchanges in the cosmos. Nothing vanishes. Everything transitions into another form of stillness, awaiting its next opportunity to return to light. The white dwarf phase also represents a lesson in equilibrium that has moved beyond energy. Its stability depends not on fusion, but on the intrinsic structure of matter itself. The electrons inside obey quantum rules that forbid them from occupying the same state, and this resistance to compression creates the counterforce to gravity. No new reactions are needed, no adjustments or cycles. The star simply exists unchanging until its remaining heat fades. In this final balance, the same laws that governed its birth and life continue to govern its rest. The story of the universe can be read as a sequence of such balances between gravity and expansion, between matter and energy, between burning and cooling. The white dwarf stands as one of the simplest and most enduring examples of that symmetry. Even at their faintest, these remnants remain part of the grand cosmic tapestry. Their soft glow contributes to the diffuse starlight that fills interstellar space. Their gravitational fields, though small, influence the orbits of nearby stars and the paths of unseen objects. Some serve as anchors in binary systems, where surviving companions still orbit a subtle reminder of the past. Others drift alone, moving slowly along the galactic plane unaffected by time. They are the silent record keepers of the Milky Way marking where stars once lived and died. In the great spiral arms, millions of them persist unseen, their quiet presence sustaining the balance of matter and motion across the galaxy. In the far future, when star formation ceases and all bright stars have long since faded, the universe will enter a phase of dimness dominated by these remnants. White dwarfs will cool into black dwarfs, neutron stars will darken, and even black holes will slowly evaporate through faint radiation. The cosmos will not end abruptly but gently, through an unending decline of temperature and light. The last visible glows will come from the cooling surfaces of ancient remnants, fading into wavelengths too long for any eye to detect. This distant era will be silent, cold, and slow, an ocean of darkness punctuated by the lingering warmth of once-living stars. In that quiet finality lies the ultimate expression of peace, a universe at rest, every process completed, every motion smoothed into equilibrium. The white dwarfs of today are the first notes of that eventual symphony of stillness, reminders that even in decline there is beauty, and that the end of light can be as gentle as its beginning. Although many stars drift through the galaxy alone, a large number exist as pairs or members of multiple systems bound together by gravity. These stellar companionships are quiet harmonies, stable over immense timescales, where two or more suns orbit around a common center of mass. Their motion determined by mutual attraction is precise and smooth, following the same laws that guide the planets, but on scales vastly greater. From Earth, such stars may appear as single points of light, their separation too small to see without magnification. Yet their presence is revealed through subtle shifts in brightness, or in the color of their light as they move toward and away from us. To imagine two stars locked in orbit around one another is to picture an unending dance performed in silence, each tracing an ellipse that keeps them in balance forever. These pairings are not rare curiosities, but common arrangements found in nearly half of all stellar systems. Binary stars display a wide range of distances and periods. Some orbit so close that their outer layers touch, exchanging material across a shared boundary. Others remain far apart, separated by hundreds or thousands of astronomical units, circling one another with unhurried grace over centuries. The closer pairs can complete an orbit in days, while the distant ones may take tens of thousands of years. Despite this variety, the principle remains identical. Gravity provides the link, and inertia provides the rhythm. The resulting motion is both dynamic and serene, the perfect example of balance in motion. Each star's path responds to the other's mass, creating a symmetry that endures long after any of the smaller details of their systems have changed. Among the most striking examples are eclipsing binaries in which one star periodically passes in front of the other from our point of view. During each transit, the combined light dips, then rises again with precise regularity. The pattern is predictable and calm, as reliable as a cosmic heartbeat. For centuries, observers have measured these cycles, finding them unchanged over generations. The regularity of their light curves is used to determine their sizes, masses, and distances, turning visual beauty into scientific measurement. Yet beyond the data lies a sense of cosmic rhythm. The gentle dimming and brightening of a binary system can seem like breathing on a stellar scale, a slow pulse that continues for millions of years without fail. Some binaries interact more dramatically, yet even their exchanges follow natural order. When one star evolves into a red giant, its expanding atmosphere may overflow its gravitational boundary, allowing gas to drift toward the companion. This transfer of matter forms a disk of glowing material spiraling between them, transforming potential chaos into structure. The flow obeys physical laws so strictly that it appears choreographed with each particle, tracing a path determined by gravity and angular momentum. In the quiet vacuum of space, such systems can persist for millennia, maintaining their balance as mass moves back and forth. What might seem from a distance like turbulence is in reality an exquisite equilibrium, where every force is countered and contained. There are even systems of 3 or more stars, hierarchical configurations, where 2 orbit closely, while a third moves around them both. These arrangements, though more complex, remain stable when distances and masses align correctly. Over long spans of time they form geometric patterns that repeat predictably like loops in a celestial tapestry. Some of the brightest points in the sky, including Alpha Centauri, belong to such systems. For any hypothetical observer on a planet within them, the sky would never be entirely dark. Multiple suns would rise and set, casting overlapping shadows and bathing worlds in hues of white gold or pale red light. The coexistence of several stars in one system demonstrates that the universe's variety often enhances rather than disturbs its calm. When viewed from afar, these companionships resemble the smallest building blocks of galaxies. Just as galaxies themselves orbit one another in clusters, so do stars mirror that structure on a smaller scale. The repetition of pattern from binary systems to spiral arms shows how balance operates universally. Each level of structure governed by gravity maintains its own slow dance of mutual attraction. There is elegance in this repetition, an unbroken continuity from the smallest pair of stars to the largest clusters of galaxies. The motions are scaled by distance and mass, but united by the same equation, ensuring that harmony persists across every layer of the cosmos. In some cases, binaries lead to new forms of light. When one of the stars becomes a white dwarf, it may draw material from its companion, heating it and producing emissions that pulse rhythmically. Systems like these, though energetic, are not chaotic. Their outbursts follow the rules of energy transfer and conservation. Each flare is followed by long intervals of quiet. Even when such systems end in supernovae, the event is part of an ordered progression, one star's end enriching the space between them, while the other continues alone or joins with the remnant in new balance. Nothing is lost from the broader perspective. Matter and motion simply rearrange themselves into different expressions of harmony. The stability of these orbits has long fascinated astronomers because it demonstrates the predictive power of natural law. Equations describing gravitational attraction allow the exact path of one star around another to be determined centuries in advance. Yet the wonder lies not in mathematics alone, but in the constancy of the phenomenon itself. These orbits have existed for millions or even billions of years, remaining unchanged by the passage of time. The stars neither collide nor drift apart. Their motion preserves both separation and unity. In this way, binary systems illustrate the same serenity found throughout stellar evolution, a balance that endures precisely because it allows motion within stability. In clusters where thousands of stars form together, gravitational interactions can temporarily bind or separate companions. Some pairs survive intact as the cluster disperses, travelling through the galaxy as twins. Others part ways, continuing their journeys alone. But whether they remain together or drift apart, the underlying principle remains unbroken. The galaxy evolves through relationships of attraction and release. The quiet exchanges of energy among stars, their orbits and separations sustain the equilibrium of the whole. On human timescales, these motions are invisible, yet across ages they shape the structure of the Milky Way, carving slow spirals that will persist long after individual stars have faded. To watch such companionships, even through imagination, is to perceive the universe as a system of cooperation rather than conflict. The stars do not compete for light or space. They share orbits and exchange matter according to immutable rules. Their existence challenges the notion of isolation. Each star, though self-contained, is part of a wider network of balance that connects all matter in motion. Gravity, the weakest of the fundamental forces, creates this unity across light years, binding even the faintest stars into quiet companionships that endure across cosmic time. If one could stand within such a system and watch its suns trace paths through the sky, the scene would unfold in majestic slowness. Two golden disks might rise together and set apart, their light blending into gentle amber twilight. Seasons would be measured not by temperature, but by the angles of illumination, the slow turn of orbits that take centuries to complete. The light from each sun would mingle with the others, creating endless variations of hue and shadow. The rhythm would be unchanging, the pace unhurried. It would be a world illuminated not by a single source, but by a partnership, a quiet demonstration that the universe finds balance not only in solitude, but also in companionship. In these stellar pairings, the cosmos expresses one of its most enduring truths, that harmony often arises from interaction, that peace is not the absence of motion, but the perfect synchronization of forces. Binary and multiple stars, though numerous and diverse, share this essence. They are the universe's slow symphonies conducted by gravity, composed in silence and performed across eternity. Their light arriving together across vast distances reminds every observer that even in the immense stillness of space, there is rhythm, relationship, and unending balance. Every star, no matter how distant, sends out a steady stream of light that carries within it a complete record of its existence. Each photon travelling across space at unchanging speed holds information about the temperature, composition, motion, and age of its source. To human eyes, this light appears as a single colour or brightness, but to instruments it reveals endless detail. When passed through a prism or a spectrograph, the light spreads into its spectrum a continuous ribbon of colour crossed by fine dark lines. Each line marks a specific wavelength absorbed by an element in the star's atmosphere. Hydrogen leaves one pattern, helium another, iron, and calcium their own distinctive traces. Together they form a precise fingerprint unique to each star. By reading these patterns, astronomers can know what lies within a sun they will never touch, separated from it by hundreds or thousands of light years. It is one of the quiet marvels of the universe that light alone, intangible and silent, can reveal so much about what it comes from. The principle is simple yet profound. Atoms interact with light in exact ways, absorbing or emitting specific colours according to their structure. These interactions remain constant across all space and time, so the same pattern seen in a laboratory on Earth can identify the same element in a star billions of kilometres away. The consistency of physics becomes a bridge across the void, linking matter separated by unimaginable distances. When a star's light arrives after years of travel, its spectrum preserves not only the memory of its source, but also the conditions of the interstellar space it crossed. Dust clouds redden the light slightly by scattering shorter wavelengths, and the stretching of the universe itself shifts the spectrum toward longer ones. By measuring these effects, scientists can trace the motion of galaxies, the expansion of space, and even the acceleration of cosmic history. Each beam of starlight thus becomes a thread in a vast interconnected tapestry of information, weaving together everything that exists into one coherent picture. Even to the unaided eye, light tells stories through colour and brightness. The deep red of Betelgeuse hints at cool surface temperatures, the white blue of Vega at intense heat, the golden hue of the Sun at balance. These differences correspond exactly to the patterns found in detailed spectra. The eye senses them as emotional warmth, but the physics beneath them is precise. The faint twinkling caused by the Earth's atmosphere adds a further layer of motion, revealing air currents that shift light moment by moment. To those who watch carefully, the stars seem alive, their flicker, a gentle reminder that light is always in motion, always changing while carrying messages of constancy. The journey of light is both physical and temporal. When photons leave a star, they begin travelling through space at the universe's ultimate speed limit. For nearby stars, the voyage takes years, for others centuries or millennia. In that time, civilizations may rise and fall, yet the photons continue unaffected by the passage of time. They carry no memory of the darkness they pass through, only the signature of their origin. When they finally reach an instrument or an eye, their journey ends in absorption, transforming energy into knowledge or perception. To look at starlight, therefore, is to witness the arrival of something ancient, a message that began long before it was received. The night sky is a living archive of the past, each star a timestamp from another era, shining simultaneously from many points in time. Because light behaves both as a wave and as a particle, it can reveal information about motion as well as composition. When a star moves toward or away from us, its light shifts in wavelength through the Doppler effect, just as sound does when a moving object passes by. A star approaching Earth shows its spectral lines shifted slightly toward blue, while a receding one shifts toward red. These minute displacements allow scientists to measure velocity with extraordinary precision. By compiling data from countless stars, astronomers map the rotation of the Milky Way and the orbits of its arms. The entire galaxy, invisible in motion to the naked eye, becomes a measurable structure through the subtle fingerprints of light. Even the expansion of the universe, discovered through the redshift of distant galaxies, is known entirely through this patient observation. The cosmos speaks only in light, and that light speaks clearly. The same principles extend to exoplanets, the unseen worlds orbiting distant stars. When a planet crosses in front of its star, the star's light dims slightly. When it passes behind, the light brightens again. By studying these changes, astronomers can determine the planet's size, orbit, and sometimes even the composition of its atmosphere. Molecules like water vapor, carbon dioxide, or methane leave faint marks in the light that passes through them. Thus, from across hundreds of light years, the chemical breath of another world can be detected. The discovery of such details through nothing more than starlight underscores the quiet power of observation. No spacecraft need travel there. The information arrives unbidden, encoded in every beam. Light also tells of the life cycle of stars themselves. In young clusters, the blue light of massive short-lived stars mixes with the golden glow of smaller, longer-lived ones, creating a collective colour that reveals age. In old galaxies where most stars have matured and cooled, the overall light shifts to red. Astronomers read these tones like chapters in a book, inferring the story of formation and evolution from the palette of starlight. Even the faint background radiation that fills the universe, detected as microwaves, carries information from the earliest moments after the Big Bang, an ancient whisper of the universe's birth still echoing today. Every wavelength tells a part of this story, and together they form a continuous narrative of energy, becoming matter, becoming light, and light revealing it all again. The constancy of light connects every observer to the cosmos. The photons striking the Earth tonight may have begun their journey when humanity was still in its earlier stages or before life itself appeared. Yet they arrive unchanged, unaffected by time's passage. They pass through atmosphere, clouds, and eyes with the same quiet purpose to reveal. Their behavior never varies. They move in straight lines at fixed speed, following laws that hold equally true in every corner of the universe. This reliability gives the cosmos its sense of order. It ensures that the same physics shaping a distant star also governs a candle's flame, that the same spectrum found in a nebula appears in laboratory light. Through this unity, existence feels continuous. Even after a star has faded or died, its light continues to travel outward. Somewhere in space, photons from stars long gone are still in motion, crossing the void toward places they will never reach. The universe in this way keeps its memory alive. Light is both messenger and record, moving endlessly until it encounters something that can receive it. To watch the night sky is to receive countless such messages simultaneously, a gentle rain of information from across time. The human eye can capture only a fragment of it, yet that fragment is enough to sense the vastness of what lies beyond. The calm of the stars comes not just from their steadiness, but from the steady flow of light that unites them. In the end, all understanding of the universe returns to this single phenomenon. Whether studying nearby suns or distant galaxies, whether seeking the origins of life or the fate of space itself, all knowledge begins with the quiet arrival of light. Its journey is the most patient in existence, its message the simplest, that energy and matter are one, and that the universe, the vast, is consistent everywhere. The information carried by light turns emptiness into connection, transforming distance into comprehension. Each ray that touches the eye completes a story that began in the heart of a star. In that soft contact between ancient light and living perception lies the final piece of the cosmos, the knowledge that nothing in the universe shines alone, and that through the continuity of light, everything remains joined in silent harmony.